Okay, so since I'm recording today, if I seem to like not, right now the camera's pointed at this side, so someone help me out. If I go to that side and I don't move it, like someone like that, hey, you should probably, so I don't like screw this up for people. All right, so now we are going to keep working with work, and we're going to start connecting it to like motion and systems and kind of like, okay, what can we do with this now? Or more importantly, kind of what can we do with energy as opposed to what we could do potentially with, just the stuff that we've had already. Why is energy kind of helping us do stuff a little bit easier? So first thing I want to do is begin with what we ended with yesterday, and that was this problem. Oh, a little smaller of an angle here. Okay, where the person was carrying a piece of luggage that had duckies in it. Just the horrible duckies.
God, duckies.
Sure, yeah.
They're like shiny.
Yeah, they were glowing or whatever. That's absolutely terrible. Anyway, so the angle here was 30 degrees. The person was pushing with a force of 120 newtons. And I said that friction over here, I think, was 60 newtons. And your job was to find the work done by all the forces in this particular situation. So, you have not yet already?
Friction is 60 newtons?
Yes.
Oh,
60
I got it.
I think that's, oh no, you also need to know that they were going to move this displacement, and you'll notice they're just, as they normally would, just put it going through the hallway of an airport or something like that, okay, 100 meters. Now, but before we get too much further, understand that this displacement of 100 meters is kind of arbitrary, okay? By arbitrary, I mean like, okay, well, they could go 100 meters. Like, is that all the distance they're going to go? No, they could probably go further than that. If they go further than that, then obviously their energies go up and up and up and up and up. Okay, it's kind of, we're just picking a displacement to go through to see how much energy it's going to take through 100 meters. Actually, let's do this to make our numbers a little bit simpler. Let's actually just go 10 meters. Let's just look at 10 meters. 10 meters is roughly here. Roughly here to the back of the classroom. I would say is about 10 meters. So obviously they're going to carry it further than that in the airport. But let's just look at that for right now. So how should you begin? Diagram, correct. If you have not yet already, please make sure and do that.
On these 16?
Yes. That should be pretty easy for you. Of course, you should have gravity down, right? Friction should be to the left. This force, we could probably call it tension, I'm guessing, would be up and to the right at an angle of 30 degrees to the horizontal. And force normal should be up, of course, and force normal should be what? Greater, less, equal to force gravity. What? Less gravity. So I'll give you guys probably, I don't know, a 3-4 minute head start to try to do this. Okay, that's probably not enough time for you to finish doing it, but I want you to do as much of it as you can on your own. You're looking for the work done by each individual force. Does anybody feel like they need any other instruction in order to get going? All right.
What would you need to know the weight or mass of the suitcase?
Nope. I don't believe that you do here, actually. Does look like there's a little bit of glare. See if that fixes anything. That's a little bit. My apologies for this next part. I have had certain songs stuck in my head the past couple of weeks. Some of them make more sense than others, but I'm just going to play at least a couple of songs that I have stuck in my head.
Here we go. Here's the first song that's been stuck in my head.
Friend is a cuddly old bear who lives with his pals in this magical book. Deep in the 100-acre wood, where Christopher Robin plays, you'll find the enchanted neighborhood of Christopher's childhood days. A donkey named Eeyore is his friend, and Kango and Little Roo. There's Rabbit and Piglet, and there's Cow, but most of all, Winnie the Pooh. Winnie the Pooh, Winnie the Pooh. Chubby little cowboy all stuffed with fluff. He's Winnie the Pooh, Winnie the Pooh. Willie every silly old bear. You can do better than that, so I'll give you more words. Let's do it. Deep in the 100-acre wood, where Christopher Robin plays, you'll find the enchanted neighborhood of Christopher's childhood days. A darky named Eeyore is his friend, and Kango and Little Roo. There's Rabbit and Piglet, and there's Cow, but most of all, Winnie the Pooh. Winnie the Pooh, Winnie the Pooh. Chubby little cubby all stuffed with fluff. He's Winnie the Pooh, Winnie the Pooh. Winnie every silly old bear. Winnie the Pooh, Winnie the Pooh. Chubby little cubby all stuffed with fluff. Winnie the Pooh, Winnie the Pooh. Winnie every silly old bear.
All right, so that's the first one that's been stuck in my head.
Oh, yeah.
But like after that,
Like
No,
most
no, hold
small
on.
boys, Christopher Robin
okay. This, of course, is the other one. This one probably makes sense.
Thank you for being a friend. Travel down the road back again. Your heart is true, so a pal and a confidant. And if you threw a party, invited everyone you knew, you would see the biggest gift would be from me. And the card attached would say, thank you for being a
So those have been stuck in my head. All right, let's see what you got. No. I don't need any more. Okay. All right. So in addition to you doing this problem, I think it should be hopefully relatively easy for you. The other thing that I really wanted to come across with is kind of like what is appropriate work to specifically show, or especially if you don't know what to do, kind of like where, especially because this is the first step that you have to understand to put the next few pieces together, and energy has like quite a few pieces. Like the last chapters that we did like all last semester had like big equations, like a grand total of like 5 or 6. I'm pretty sure this chapter alone has about 11 or 12 different equations, okay? So like this is just the beginning, which is why I kind of want to make sure that you're doing this stuff appropriately. So if we're talking about, let's go with this guy right here. So if I want work of tension, what you're going to write is this is equal to force of tension times displacement times cosine of angle of tension. Couple things to point out. Why is tension got a subscript on both force and angle, but not on displacement? displacement should be the exact same for absolutely all of them. Yeah, it's just how far the object is going in general, which is why that's not the case. The subscript on the angle, of course, is because all of the forces potentially have different angles, okay? I showed you yesterday how to shortcut a couple of these equations, and I'll show it to you again, but I'll also make sure that you know how to do it kind of mathematically to show kind of that calculation in a second. I shouldn't have skipped ahead. I'm talking about force normal and force gravity right now. All right, but this, of course, is just going to be 120 newtons times 10 meters times the cosine of what should the angle be? Should be 30 degrees. Yeah. Now, why should it? I gave you 30. Why should it be 30? Where's the angle measured between?
The displacement.
Right. The displacement is this way. The force is that way. So that's where the angle it gives you is in fact the angle that you need. That's not always going to be the case. So do make sure that you check that. After plugging that in, this should be what? Like 12,000 cosine of that? What would you get?
1039.2.
What's that?
1039.2.
1039. So 1,039.2. Let's just go 1,039. Okay, at that big of a number, and the units on that should be joules. Okay, I'm going to skip over here to friction. Actually, no, we'll go around the circle. Let's go to work of normal. Nope. Let's go to work of gravity. All right. So this is going to be force of gravity times displacement times cosine theta of gravity. And of course, yesterday I told you, what is the final answer to this one?
0.
0, of course. Why is it 0? Mathematically, why is it 0? Because it's going to be the cosine of 90 degrees, and of course that's 0. Conceptually, why is it 0?
There's no X.
You're still kind of answering it mathematically a little bit. So when I say conceptually, what I'm saying is essentially, what does it mean that gravity is doing no work? Well, for starters, work is what?
Change in energy.
Change in energy, right? That's what I'm looking at. Not the equation, but it's the change in energy, right? So when I say work is 0, this is important because some people screw this up. Am I saying that the force is 0? No, it is absolutely still pushing. When I say that work is 0, what we're saying is that, hey, this force is pushing down. Is it actually going the way that we expect it to go? No. Is it going against the way we expect it to go? No, absolutely not. So it's not going to do anything as far as its energy is concerned. It should not affect the energy of that object. Does that make sense? Okay. So if you knew, I was going to try to show this mathematically, but actually Victor did point out that I didn't give mass or weight. Let me just do that real quick. Let's say force of gravity had been 10 newtons. Actually, let's go 30. Okay, 30 newtons. If I wanted you to really play this out mathematically, here's what it would look like. You'd still go 30 newtons. You'd still say 10 meters, but of course cosine of 90 degrees over here makes the other two a moot point, because of course that makes everything 0. So that's 0 joules. Going around the corner to friction, work of friction is going to be force of friction times displacement times cosine theta of friction. Force of friction, of course, being that 60 newtons times 10 meters times cosine of what angle? 180. Again, I want to remind you and point out, notice that neither the force or the displacement are negative in this equation whatsoever, because remember, this is a scalar thing that we're calculating. And for work of normal, you actually, again, we don't know what force normal is. If I wanted to find force normal, yes, you will have to do some of that stuff from last chapter. You'd have to sum the forces and treat it like a vector and still use all that stuff. But do we really need to go find force normal in order to calculate this? No, because it's the same sort of thing again. So let me use this opportunity to show you the shortcut. And that is work of normal, just say, hey, it's 0 joules. And then kind of for an explanation of why, I would say because force normal is perpendicular to displacement. Make sense? Okay. Now, here's what I want you guys to do in the next 5 to 10 minutes. The next piece of this is I really want to make sure that these numbers somewhat make sense to you, and that you get a gist of using this stuff in real life, not just like major problems. I mean, like if you walk around today. So here's what I want you to do. In your group, and actually, Rebecca, I'm just going to have you kind of just work with them or move over. You don't have to necessarily move, but you'll work with them. In your group, I want you to do the following, okay? Calculate how much energy it takes you to walk up one set of stairs here at school.
You know, an entire floor.
I'm not going to tell you any numbers. I'm going to have you guys make up what numbers are relatively correct. They don't have to be perfect, but so don't like stress over like obviously is the distance 1 meter or is it 1.2 meters? At that point, who the heck cares? It's get pretty close, but see what you guys can do. See if you can't figure out how much energy does it take you to walk up the set of stairs. Or if I can say this potentially in a way that maybe makes a little bit more sense given what we just said, how much work does your body do to get to walk up the stairs? Yep, 1 floor's worth. So like if you were to walk from that main area right down and you come into the front of the building, straight up the stairs there till that spot where you're going to be by the freshman office, just that set of stairs, how much energy are you going to use? Yes?
Yeah. We have to use a.
I am telling you everything you're trying to figure out. There you go. I apologize online. This is not a terribly interesting thing, but what you might try to do real quick, hold on, I'm talking to the camera. Okay, what you might try to do is try to do this. You can pause or whatever and skip ahead. I'm not entirely sure how long it's going to take, but see if you can't do it yourself before us coming together and talking about it. Sorry, Peter, go ahead.
So it's like, are you wanting us to solve for all of the forces?
I want you to calculate how much energy it takes you to walk up the stairs from like the first floor to the second floor, or the second floor to the third floor.
You go. No.
And so to answer your question, you kind of got to figure what your question out.
It didn't mean it. I realized it.
No, I was talking to
Oh,
Peter.
you're looking.
I was talking to Peter. Well, you guys are very close.
Okay.
I tell you what, I'll make sure with it, I'm going to let you guys start, try to figure it out as much as possible. I promise to answer all the questions to make sure that you see it towards the middle or end. You will eventually see it from me, making sure, but I want you to do your best.
If we find
Right there.
which I would say
So the stairs from the second and third floor.
Continuing in the idea of songs that get stuck in Spainhour's head. I don't know if this even counts as a song. No, it doesn't.
Wait, where it's on this like 3 meters. Set on an angle. I like Going from pounds to newtons, like that would be 39.
Pounds to newtons? Pounds to newtons is a conversion.
Oh, that's why it's so low. So what's 70 pounds?
Pounds and newtons are both a measurement of force. Mass is, of course, the unit of measure for inertia and gravity. That's the one that you multiply by g. If you haven't yet, you make me sad. What is the first thing that you should probably do in a problem?
Draw a picture.
Yeah, force diagram picture. If it helps you, couple things, okay? One, is there friction? Yes. Should you probably have friction in your force diagram? Like, is it going to be significant to this situation? No. You're not moving very fast. So you're only overcomplicating it. And when you're looking at something like this, you want to try to keep it stuff that makes sense, okay? A question was asked earlier that I will now answer, or you should answer. Is it reasonable, or should you probably assume a constant velocity? Is it fair that most of you guys probably climb the stairs at a constant velocity for the most part? Yeah.
What about the force normal?
Now, there's an interesting thing there between force normal, okay? The push upwards is, yes, force normal, but the one you're worried about is actually like your legs pushing on it, which is kind of that equal and opposite. So like the force normal up, what I would do instead of force normal up is say like force muscles on person up, something like that. But yeah, your force diagram should hopefully be pretty darn easy, given that it's a constant velocity. This one. Another sign that gets stuck in my head regularly.
Sounds familiar. Yes.
Eleanor.
Where are we at as far as an answer? We got an answer. We're
Yeah.
need a few minutes. Where are we at? Need help?
We got 3. Do you want like the order?
What do you mean all three?
Like, do you want the individual words?
Here's what I want. I want to know how much energy it takes you to climb the stairs, like one set of stairs.
Got it, okay.
Okay, we need the.
All right. Actually, I'm gonna stop you guys here. I want to make sure I'm not getting people too far confused, and we're seeing kind of this problem is actually, with knowledge, relatively easy. Okay. It seems like a lot of people are somewhat confused. So let's put ourselves like, what are some ideas? Where did you start? Force diagram. Okay, so you probably drew some stairs, right? Nailed it. All right. And force diagram. Who did you draw? What did you draw the force diagram on? Person. Okay. All right. What was your force diagram?
Force gravity down.
Force gravity down.
And force muscles on person.
Force what? Yeah. Force muscles on person up. Now, pretty darn easy. That seems a little bit weird, but I mean, consider this, right? This guy right here, when it's going at a constant velocity across the room, what's its force diagram?
Smart.
Gravity down and normal up. Do you need a force in the direction that you're going in order to stay going? No, because it's the first law of inertia. Now, one thing that is, of course, true that would mean that your muscles need to push. Well, definitely your muscles are pushing against gravity here, but also a little bit of friction. You're going to have to resist against that. But for the most part, that's pretty good. The nice thing about this force diagram is real quickly you see that my force of muscles on person basically has to be equal to force gravity. Now, obviously, this does mean that all of your definitely muscles pushing on this have to be different because all of you have to push a different amount because all of you guys have different weight because all of you have different amounts of mass or amount of atoms that make you up. Okay, but let's just pick a size of person. Doesn't have to be you, just anything. Pick a size of a person. Give me somebody's weight.
Let's say 150.
150? I'm going to make it a little bit different. Let's go 160. Okay, 160 pounds. Now, of course, a quick conversion is probably going to be necessary because we need this in newtons. Now, if you decided to go for mass or start in newtons, no problem. If you think that's pretty accurate, you're okay. But 160 pounds, well, I know that in 1 pound there is 4.45 newtons, and I'm picking 160, or I pushed you to do that because I did it earlier, and that's about 712 newtons. Everybody good so far? All right. Now, I want to show you what I did, and I'm going to guess what you did and made your life a lot more complicated. For starters, when I ask how much energy you spent to climb the stairs, what mathematically, or what am I asking for in terms of science variables?
Net force.
No.
No.
How much energy, I asked you how much energy it takes you to climb the stairs.
You want the work?
I want work. What do I want to work, what?
Do you want the work of force normal?
Oh, close. I want the work of muscles on person. Right. Do I care about the work net?
No.
No, as a matter of fact, you guys already know what is the work net. 0. Because
Pushing up.
Net force is 0.
net force is 0, as well as, going at a constant velocity this entire time. Okay. Now, here's what I did. What I did is I said, hey, I think the stairs are about 3 meters tall, ish. Okay. And then I stopped because I imagine what a lot of you guys tried to do is you guys try to guess or figure out what that angle was. Yes. So that you could use the equation work equals force times displacement times cosine theta. However, if you'll remember our conversation over here yesterday, and I'm going to put it up here for the sake of the camera, I said, hey, displacement is here, force B is like right here. What was the reason for the cosine of the angle? Why did we do the cosine of the angle? What was it meant if this was force B, and we're trying to find the work of this force, and this is my angle, what is that cosine meant to do? What'd you say? It was meant to get the force that is in the same, the force in the same direction, right? But look at these guys right here. Are they already in the same direction? Yeah, so let me put this in perspective. Let's say that this right here was, for the sake of simplicity, 4 meters. Okay, basic triangle, that would mean that that is 5 meters. Okay. If you did that, you would get that this guy is the smaller one, 37-ish. I think 36.9, but I'm just making up some numbers here, right? So if you did this, okay, you would plug in that the force was about 712 newtons, okay? The displacement would be what if you had done this? What would be the displacement? 5 meters, correct? And the angle would be what? 37. But look at this real quick, because this is very important for your understanding moving forward. And actually, I'm trying to make life simpler for you going forward. Punch this into your calculator real quick. 5 cosine of 37. Wait. That's not right. I did it wrong. I'm sorry. I screwed up. That's not going to say the right thing. I gave the wrong angle. Why did I give the wrong angle? What's that?
It's a 3.5.
No, that is the right angle for the 3, 4, 5. But I gave the wrong angle because what?
How are you doing it from that?
I'm doing it from, where should the angle be put? with the vertical because it's from the force to the displacement. So actually the angle that you should use is this one. So we should use 53, correct. So just change what I say here to 53. What is 5 meters cosine of 53? So did we really need to do all this work to know that the force goes 3 meters in the same direction here? So let me change this equation kind of, okay? Basically, its full equation is F times displacement times cosine theta. However, the purpose of the cosine theta is to make sure how much of force is going in the direction of displacement or how much displacement is going in the direction of force. So another way to put this is this. Work is the force that is parallel to the displacement. Meaning, I don't need to worry about the angle at all if I already know the distance in that direction. Does that make sense? Let me give you another for instance real quick. If there was, say, a ramp, okay, right here, and there was a ball that was going to roll down the ramp, and I wanted to know exactly how much force of gravity was going to do work. Let's say, for sake of argument here, force of gravity is 1 Newton. Let's say that is, I don't know, 2 meters, something like that. And this over here is, let's go 1 meter. Okay? I could find the angle here, and I could punch in 1 Newton times 2 meters times cosine of the angle, right? But the displacement times cosine of the angle is trying to tell me this. How much distance is in the same direction as the force, right? So instead, what I would do here is I would say work is 1 Newton. The displacement that is parallel to that is 1 meter. And if you will, just take the angle between those two. What's the angle between gravity and this displacement? 0. Cosine of 0, of course, is 1, so you can just use this right here to get that that would just be 1 joule. Does that make sense? So let's finish this problem over here real quick and show it to you relatively easy. The work done by muscles on person is equal to force of muscles on person times the displacement that is parallel. So 712 newtons times 3 meters, or 2,136 joules. Questions about that? Give me, if I told you this again, or if I asked you something similar to this, give me a 1 to 5. How comfortable do you think you would be to figure out how much energy that you spend going up the stairs? Thank you. Okay. Now, next thing I want to point out is this. You guys are probably not necessarily used to joules, unless you've done a decent amount over in chemistry and energy work right over there, in which case you probably might be. But I do want to tell you what you are a little bit more used to, and that, of course, is calories. So next question is, Spainhour, how many calories did I just burn climbing the stairs as a 160-pound person? Well, the amount of calories that you would specifically burn, well, we need a conversion, because 1 calorie, that's a small calorie, is equal to 4.2 joules. However, that's not the calories that you usually hear. Those are small c calories. Okay? Those are used oftentimes in chemistry, but when you hear calories in terms of like nutrition and stuff, that's actually not it. They say calories on your cereal boxes, on pretty much all nutritional values, but what actually they mean is capital C calories, otherwise known as a kilocalorie. And so if they say that a soda has 160 calories, they're really saying that it has 160 kilocalories, meaning it's equal to 4,200 joules. So, how many calories did somebody burn climbing that particular set of stairs? 2136 divided by 4,200. About half a calorie. Meaning, okay, if you just drank a soda at lunch, 160 calories, okay, all you got to do to burn off that soda is, of course, climb the stairs 320 times, okay, and that would burn off 1 soda. Now, this, of course, is why you have other processes that burn it. But it's why if you ever work out, it's always a really sad conversation on whether or how many calories you actually burn at that particular time. I did a few years ago. I was working out kind of consistently, and I had this app that told me how many total pounds I lifted that particular day, and it was a good day because I lifted legs, and so I lifted something like 12,000 pounds or something like that, and it made me feel good, right? 12,000, but at several different times. So I lifted 12,000 pounds, and I was thinking to myself, all right, let's assume that when I lifted, this isn't very far, and this isn't, I'm not a very large human being, but okay, let's roughly say every time I lifted, for the most part, I lifted roughly half a meter, okay? So what I did is I go, all right, well, 12,000 pounds multiplied by 4.45, because I'm a giant nerd, I lifted 53,400 newtons, okay? And if I lifted them about a half a meter, okay, times 0.5, it means I just used 26,700 joules, which sounds amazing until, I used about 6 calories. Or about 6 calories in the gym, which is why you should take care of nutrition more necessarily than exercising, but also exercise, it's a whole other thing. Okay, what I want to do now is I want to talk about this. Let's get rid of this. First thing I want to talk about is work net versus individual works. There are 2 ways to calculate work net. Work net is the total work. This is usually the symbol used. I remembered. Okay, this is usually what we'll use for total work on the situation. To give you an idea, though, we could technically, to put it very similar to last chapter, say that this is the sum of works. Okay. The main reason we don't, it's not a big problem, but basically I think the reason they switch these is to give you an idea that basically when this is used, you usually expect to be doing vector addition, and when it's just net, for the most part, usually you're talking about adding them all up. But if you went to some other textbook, you could see sum of forces that we talked about last chapter also be listing as force net. Just basically add them all up as opposed to worried about the individual ones. So, how do we calculate work net? There are 2 ways. Okay, the first way is really, really simple, and it's this. Because energy is scalar, you just add up all of them. However many works there are, add them up. The second way is as follows. By the way, let's put the equation for work up here. A kind of our new sort of equation, but not really. This is what you would use if force and displacement are not parallel to each other. Yes, you need to figure out their angle. If they are parallel to each other, you can really just multiply the 2 of them together. The second way of getting work net should look very familiar because essentially it's just do this again, but guess what force you're going to use? Yeah, the sum of forces. So it's kind of weird here. So I could say force net times displacement times this would be the angle with the net force, or since we did this last chapter, we would use that instead. To show that this is in fact the case, let me go ahead and bring up that last problem again real quick. If I was really smart, I wouldn't have erased it. But do that while you guys are writing that stuff down. So we know, of course, that work normal was equal to 0 joules, work of gravity equal to 0 joules, work of tension, remind me what that was. 120 newtons times 10 meters times the cosine of 30 was what? What's that? Yeah. Okay. 10,039 joules. And then work of friction was what?
Negative 600.
Why does it make sense that friction was negative?
It's going the opposite direction of the displacement.
Right, so it's basically taking, does it make sense that friction is constantly taking energy out of objects? It should. So, according to this, according to this right here, what I'm trying to point out is if I want the work net, I can either do this, just add work of normal, plus work of gravity, plus work of tension, plus work of friction. In this case, of course, that is nice, that's 0, and this is 1039 plus a negative 600 joules for a total of 439 joules. Or, I'll show you this. Remember that sum the forces in the x. What is the net force? Well, the net force would only be in the x, right? Because it's only accelerating that way. So the force in the x would be force tension in the x minus force friction, right? Which would be 120 newtons cosine of 30 degrees minus 60 newtons. And if I'm not mistaken, it should be 43.9 newtons. Let's go ahead and check that real fast. 120 cosine of 30 minus 60. Yep, 43.9 newtons. Everybody got this? This makes sense. You guys did this last chapter. I'm not forcing you to do it right now, but you could totally do it very easily. Yes? Why didn't I do anything in the y?
It's not necessary.
Yeah, because it's canceling out. We know it's accelerating that way, so we know the net force is also that way. So what I'm showing here is we could use this equation, or we could also force net is 43.9 newtons times 10 meters times cosine of, what would the angle be between the net force and the displacement? 0. Sorry, that looks like a negative. It's just supposed to be an equal sign. So that's 1. So you can see they end up the exact same way. Now I do this, of course, to show you that you can use either method, okay? But this you do not have to do both of these most of the time. Do whichever one is easier for you, okay? Now what students tend to do is they tend to pick one, and they say that that one is easier and stick by it. Usually I would say it's probably this one, and this is probably the one that you'll see me use most often. I will tell you right now, you kind of got to think about both and maybe force yourself to use both, especially towards the beginning, because there are definitely some problems that this is easier, and there are definitely some problems where this is easier. And if you only make sure that, learn one of them, obviously you're going to forget the other one and make your life a lot more complicated moving forward. Make sense? All right. Last piece of this puzzle to put together is this. I told you two things towards the beginning. One, I said that we were weirdly starting with this one, right? You remember why I said that? When talking about energy, we talked about the change in energy first. The change in energy, of course, is work. This is work. We have not talked about types of energy or energy because there's like 11 of them. We are going to talk about one major type of energy right now. The other thing that I told you is that what is kind of your hint? What is your hint on whether or not energy is in fact changing? What's that? Speed, right. Watch speed to see what energy does. So, based on this, since there is a force net in this problem, okay, what would you expect this suitcase to do the entire time? What's that? Think about speed. If we're adding energy into this suitcase, more and more and more energy, what would you expect the suitcase to then do?
Accelerate.
Yeah, increase its speed. What would we expect that to be if it were staying at a constant? 0. That being said, what is probably unrealistic about the problem that I gave you? Yeah, it probably... Is somebody going to apply force enough to accelerate the entire time they're going through the airport? No, absolutely not. They are not going to keep applying force And you can see here that there is a net force already, so it should accelerate, which maps kind of nicely over here. So what I want to show you right now is what this work net is actually equal to, and it's one of the changes in type of energy over here. Work net is equal to the change in kinetic energy. You'll remember that kinetic. Kina is a base word that means, does anybody remember? Moving. So that's really just saying the energy associated with moving. Okay? We will talk more in detail a little bit later on about why this equation is the way that it is, but let's talk about this equation real quick. Kinetic energy. If you had to guess, what is probably the main value that we would look at in terms of kinetic energy? What's that? I got you. Would you guess that I have kinetic energy right now? No. Would I have kinetic energy right now? Motion. Or how would we measure motion? Speed. Speed in this case. I'm just going to give you the equation real quick. We'll talk more on Monday. It is 1/2 mv squared. All right, guys. I will talk to you guys on Monday.